In section 3.2, we look at concavity and points of inflection. And so let's start with our definition of concave up and concave down. And this basically comes from the first derivative. And it says, if the first derivative of a function f is increasing, then we say that f is concave up. And alternatively, if f prime is decreasing, then f is concave down. Now, make sure you understand the difference between the statement if f is increasing and if f prime is increasing. In the previous section, we used f prime to determine when f was increasing by finding when f prime was positive or negative for decreasing. But here we're actually looking at the derivative and seeing how the derivative is changing. So in this case, the derivative is increasing or the derivative is decreasing. That's not the function itself. The function f could be increasing or decreasing while f prime is increasing only. And so this is what we call concavity. Now basically concavity relates to how the curve sort of opens up. And you've done this in college algebra. When you look at a curve like the parabola, you would say that this opens up. Well, that's now concave up. And something like this is concave down. So if it makes the bowl shape going down, then it's concave down. If it makes the bowl shape going up, then it's concave up. Let's look at a little example here. Let me draw in sort of a little function here. That's an example of concave up. And what I'm going to do in red is I'm going to draw the slopes of the tangent lines at various points. Now, these aren't exactly accurate, but they just sort of give you an idea about what's going on. If you take the tangent line at this point, then we can say that that has a slope of maybe -3. It's definitely going down. It's pretty steep. Let's say -3. If I come to this point over here, then this tangent line is still slanted down, so it's definitely negative, but it's not as steep as the previous one. So let's call that one -1. These are just estimates. At this point, we have a horizontal tangent line, so that would be 0. And then at this point here, the slope is going up, so let's say that that's +1. And then at this point, relative to the previous point, it's definitely much steeper, and we'll say that that's 3. And those are just estimates to give you an idea. Now, if you sort of think about this as you go around the curve from left to right, the numbers start at -3, then they go to -1 and 0, 1, and 3. And those numbers are increasing. So we will say that f prime is increasing. And when f prime is increasing, that tells us that the original function f is concave up. Now similarly, I could draw another curve over here, and we could do sort of the same thing. We'll go ahead and put in the slopes here. So a slope at this point right here, it's pretty steep. We'll say that that's +3. And a slope here, about 1. A slope here at the top, that's horizontal. So that would be 0. And then as we keep going, now we're coming back down here. So this slope could be -1, and this slope here would be -3. And of course, these slopes come from the first derivative. Now, if I do the same thing as before, and I sort of trace around going from left to right, the numbers go from 3 to 1 to 0 to -1 to -3. These numbers are getting smaller. So we say that f prime is decreasing. which then tells us that f itself is concave down. Let's take a look at determine intervals where a function is concave up or down. So this is the how to do these problems sort of thing. And it's similar to the list that we had in the previous section. Part 1, find the values of x where the second derivative is 0 or the second derivative is undefined. Find the partition points to make a sign chart. And then these values and any points that separate the function because of the domain. So you find the values that the second derivative is 0 or undefined, and any other points that split up the domain, those are the ones you use to make the sign chart. Step 3, make the sign chart by testing points inside each interval created by the partition points. And then if the second derivative is positive, then we have concave up. If the second derivative is negative, we have concave down. And then any point on the graph where the function changes concavity is called an inflection point. But it does have to be a point on the graph. It can't be an asymptote or something like that. Let's look at example number 1. Determine the concavity of f of x is equal to negative x cubed minus 6x squared plus 18x plus 5. So we're going to need the second derivative for concavity. So always remember that. Second derivative gives us the concavity. And so to do that, we need to find the first derivative. And the derivative of this function would be negative 3x squared minus 12x plus 18. And then let's take a second derivative. So that would be negative 6x minus 12. Now we need to find where this function is equal to 0 and also where it is undefined. Well, since it's a linear function, negative 6x minus 12, it's never undefined. So all we need to do now is just set it equal to 0 and solve for x. So we're going to get negative 6x is equal to 12, and x is equal to negative 2. Now we can make a sign chart, and we'll put our value, our partition point, on the sign chart. It's negative 2. We're testing f prime, and these are the x's. It was a 0 with f prime, so we mark that with a 0. And then we need to do some testing. So I will test at 0, let's say. And so if I do f double prime of 0, I get negative 6 times 0 minus 12, which is equal to negative 12. So the interval from negative 2 to infinity has a negative second derivative. And then you can test this one, or you can use the multiplicity rules. I'll test it at negative 5, maybe. This would be negative 6 times negative 5 minus 12. And that would be 30 minus 12 is positive 18. So this interval is positive. So that tells us that f is concave up on the first interval and concave down on the second interval, and that negative 2 is the location of an inflection point. So we can write that in 3 simple statements. F is concave up on negative infinity to negative 2. F is concave down on negative 2 to infinity. And F has an inflection point at negative 2, comma, and let's say negative 47. And this negative 47, this just comes from evaluating the original function at negative 2. So you plug that into the original function to find the exact point on the curve where it changes concavity. Example number 2. Determine the concavity of f of x is equal to x to the 5th minus 3x to the 6th plus 27, and find its inflection points. So again, let's start by finding the first and second derivative. So we'll have 5x to the 4th minus 18x to the 5th. And the second derivative is 20x cubed minus 90x to the 4th. Let's set that equal to 0 and solve for x. So the question is, what can I factor out? And from the numbers 20 and 90, I can factor out 10. And from the x's, I have x cubed and x to the 4th, so I can factor out x cubed. That leaves me with 2 minus 9x equal to 0. Then we can split this up, set all three factors equal to 0, and solve for x. So I get 10 equals 0. Nope, not going to happen. I have x cubed is equal to 0, which gives me x equals 0 with multiplicity of 3. Recall that the multiplicity comes from the exponent of the factor that gave you the solution. Finally, we have 2 minus 9x equals 0. And if we solve for x, we get 2/9. Now this has multiplicity 1 because the factor that gave us this 0 had an exponent of 1. Even though it wasn't written, it really was a 1. Next, let's draw our sign chart. So we have x, and we're testing f prime. We have 2 zeros to put on the sign chart. We have x equals 0, and we have x is equal to 2/9. And these were zeros of the second derivative, so we'll mark those with zeros. And then we need to test some values. I'm going to test the value that's right in the middle of both of these, which is actually 1/9. It's halfway between 0 and 2/9. And a number that's halfway between 0 and a number n is always half of n. Well, half of 2/9 is 1/9. So we know that that one does work down in there. When you do the testing, let's bring that up here. Oops. So let's do f double prime of 1/9 would be 10 times 1/9 cubed times 2 minus 9 times 1/9. And all we're testing for is the sign. So 10 is positive, and 1/9 cubed is positive. And then let's see what happens here. 9 divided by 9 is just 1, and so 1 times 1 is 1, and 2 minus 1 is 1. So this is positive. So I have 3 positive numbers multiplied together. That gives me a positive. And the multiplicity of 2/9 was 1. That's odd. That means it changes when we cross over. The multiplicity at 0 was odd as well. So when it crosses over 0, it changes multiplicity there as well. And there you have it. So we now know that f is concave down, and then concave up, and then concave down again. And we can write that in a statement. So f is concave up on 0 to 2/9. F is concave down on negative infinity to 0 union 2/9 to infinity. And then f has an inflection point at x equals 0 and x equals 2/9. So both of those numbers resulted in a change in concavity, therefore they're both inflection points. Technically you should find the y value, but the y value for the 2/9 one is very complicated, so we're just going to skip that on this one. Example 3. Determine the concavity of f of x is equal to -5 times x minus 2 raised to the 2/5 power. All right, so again, looking for concavity means we need the second derivative. So we start with the first derivative. And the -5 out in front is a multiplier, so it stays there. Now I'm going to take the derivative of the rest of this. It's a power rule followed by a chain rule, although the chain rule doesn't do too much. So we bring the 2/5 down. X minus 2 stays the same. Lower the power by 1. So 2/5 minus 1 is -3/5 times the derivative of the inside, which is just 1. And then we simplify. So -5 times 5 cancels and leaves me with a negative. So this is -2 times x minus 2 to the -3/5. Next, I need the second derivative. The -2 in front is a multiplier again, so we're going to leave that there. And then we're going to find the derivative of the rest of this using the power rule and the chain rule again. So we bring down the -3/5 times x minus 2, lower the power by 1 to -8/5 times the derivative of the inside, which is just 1, by the chain rule. And then let's see if we can simplify. So -2 times -3 is +6. The 5 is in the denominator. And the x minus 2 to the -8/5, because of the negative exponent, is going to go down into the denominator. When it goes down into the denominator, the exponent changes to a positive. And I needed to do that in this case. I didn't want to do it before in the first derivative because I was still taking derivatives. You don't want to simplify it to the final format until you're finished taking derivatives, unless you need it for something else. But here we want to do that so that we can actually see what's going to happen here. Remember that the partition points we need to find for our sign chart to determine concavity come from two different sources. They come from where f double prime is equal to 0 and where f double prime is undefined. Well, in this case, if we wanted to find where f double prime is equal to 0, you would just set the numerator equal to 0. Well, the numerator is just 6. There's no x's up there, so this yields no solutions. Now to find where f double prime is undefined, you would set the denominator equal to 0. And now you solve this for x. So the first thing I would do is divide by 5. 0 divided by 5 is still 0. Next, I would raise both sides to the reciprocal exponent. So that is 5/8. That gets rid of the exponent on the left side, and then 0 to the 5/8, still just 0. And there's really no need for parentheses here. Let me just go ahead and wipe those out. And there you have it. X is equal to 2. And this is the only value that we're going to use for the sign chart. Let's go ahead and make our sign chart. We have one value. it's a 2, and it is undefined in the second derivative. Now we should point out that it's still defined for the function itself. All right, let's do some testing here. I'm going to test at 0. So f double prime of 0 would be 6 divided by 5 times 0 minus 2 raised to the 8/5 power. And this would be equal to 6 over 5 times negative 2 to the 8/5 power. Now I don't know what negative 2 to the 8/5 power is, but I do know that we've got an 8 sitting right there. And that's great news for us. Because that is even, that means whatever this really turns out to be is always going to be positive. It's the same rule. For example, if you square a positive or a negative number, you always get a positive number. So this number is positive, the 6 is positive, the 5 is positive, everything is positive. So this is positive over positive times positive, which is positive. And that was at 0, so that's on the left side. But there was nothing special about the negative 2 here from the 0. This is always even, so this is always positive. So it's going to be positive over here as well. And that tells me the following information. F is concave up on negative infinity to 2, union 2 to infinity. F is never concave down. And F has an inflection point at 2, 0. And again, this comes from doing f of 2, the original function with the value of 2. Now let's make sure that we understand why this does have an inflection point. The function is defined at 2 even though its second derivative is undefined. It was originally defined at 2, so it does have a point there where it changes its inflection. Let's draw the picture here, and you can sort of see what this looks like. So here's 2, 0, and this function looks like this. It goes up, it's a little bird, and then comes down like that. And it's concave up over here, and it's concave up over here. Example number 4. Determine the concavity of f of x is equal to x minus 1 over x squared minus 4x plus 5, and find the inflection points. So for this problem, since it's a rational function, I want to start by finding the domain. And so to find the domain, what I have to be worried about is whether or not this denominator is equal to 0. And so what we're going to do is we're going to set it equal to 0. And you want to solve this. Now you might try factoring it, but it doesn't factor. And so I'm going to do something else. I'm going to do complete the square. To figure out what the solutions are. So to complete the square, the first thing you do is you make sure that the lead coefficient is 1. If it's not, you need to factor that out from the first 2 terms. In this case, it is. So we're going to write this as x squared minus 4x, and then we're going to put in a blank, and then we're going to put the 5 over here with another blank. Well, these blanks are going to be filled with 2 numbers. The 2 numbers will be opposite, and one will be positive and one will be negative, so that way they will cancel and won't add anything to the expression. Now to complete the square, we need to figure out what number should go in the blank in order to turn this expression into a perfect square. And the way you do that is you start with the coefficient of the x term and take 1/2 of that, and that's a 2. And then you take this 2 and you square it. and you get a 4. So we're going to add 4 to the left part here, and to balance that, we're going to subtract 4 from the right side. When we do that, this piece that I've underlined here factors into x minus 2 squared, and then 5 minus 4 is 1. And it's still all equal to 0. So that's completing the square. We're going to use that to solve this equation. The next step in solving this would be to move the 1 to the right side. And that gives me x minus 2 squared equals negative 1. And there's the problem. You can't square a value and have it equal to a negative. So therefore, there are no solutions to this equation. Since there were no solutions, that means the domain does not have any bad points where it's undefined. And so the domain is all real numbers. We might need that going forward later on. Now let's get to the derivatives and the concavity and such. So let me go ahead and rewrite the function. F of x is equal to x minus 1 over x squared minus 4x plus 5. And now let's take some derivatives here. Let's start with the first derivative. We need to use the quotient rule to find this derivative. So it's the derivative of the top times the bottom unchanged minus the derivative of the bottom, 2x minus 4, times the top unchanged, all divided by the bottom squared. And now we need to simplify. So this is going to be x squared minus 4x plus 5 minus, and now I'm going to use FOIL to multiply this out. So that would be 2x squared minus 2x minus 4x plus 4 divided by x squared minus 4x plus 5 squared. This gives me x squared minus 4x plus 5. I'm going to distribute the negative, and I'm going to combine these two like terms in the center. So it's going to be negative 2x squared. This should be negative 6x, but the negative distributes and makes it positive 6x. And then we have positive 4, distribute the negative, it becomes negative 4. The bottom is the same. And then we combine. We get negative x squared plus 2x plus 1 divided by x squared minus 4x plus 5 squared. And that's the first derivative. Put a little box around that. Now let's find the second derivative. And we'll take the derivative of the first derivative. It's a quotient rule, but notice that the bottom has a power and an expression. So that's going to be the chain rule on that. Well, let's go ahead and take the derivative using the quotient rule. So it's the derivative of the top. It's negative 2x plus 2 times the entire bottom unchanged, x squared minus 4x plus 5 squared, minus the derivative of the bottom. To find the derivative of the bottom, we're going to use a power rule. So it's 2 times x squared minus 4x plus 5 raised to the first power, because we lower the power by 1, times the derivative of the inside by the chain rule. The derivative of that inside is 2x minus 4. And then times the numerator unchanged, negative x squared plus 2x plus 1. All of that is divided by x squared minus 4x plus 5. And the original power here was a 2. And now we're going to square that, and 2 times 2 is 4. Now we have to simplify. The one thing that I noticed that we can factor out here is that we both terms here have x squared minus 4x plus 5. And so the first one on the left has a power of 2. The one on the right has a power of 1. So that means we can take out 1 power of those. So let me do that here. This is x squared minus 4x plus 5. And then that's going to leave behind negative 2x plus 2 times the remaining power, x squared minus 4x plus 5, minus the 2. And then this term has been removed already. And so, but that leaves us with 2x minus 4, and it leaves us with negative x squared plus 2x plus 1 over x squared minus 4x plus 5 to the 4th. Now when we go to simplify this, we see that we have x squared minus 4x plus 5 on both the top and the bottom. There's 1 power here on the outside. That is going to cancel with the 4 powers on the bottom and leave us with a power of 3. Our next step is to simplify this into a rational simplified function. So what we're going to do is we're going to start by multiplying the 2 parts together. So on the left side here, I'm going to start with the 2x, the negative 2x, and multiply that through. So that's going to be negative 2x cubed plus 8x squared minus 10x. Next, I'm going to multiply 2 times every term. That's going to give me plus 2x squared minus 8x plus 10. And now I'm going to work on the right part. The first thing I'm going to do is I'm going to take this one little step at a time. I'm going to multiply the 2 into just this first term. This 2 does not distribute to both the first term and the second term. It does not do that. It only distributes to one of them. Distribute is not even the right word. It multiplies into one of them because they're all factors, right? So when you have 3 factors and you multiply them together, you just multiply them all together. So this is going to be 2 times 2x is 4x minus 8. That's all still divided by x squared minus 4x plus 5 to the 3rd power. Next, let me take the terms on the left and simplify what I can. So this is going to be negative 2x cubed. I'm looking at the x squareds, and I see I have 8 and 2, so that's 10x squared. Looking at the x terms, I have negative 10 and negative 8, so that's negative 18x. And then the constant term is just 10. Now I need to multiply the rest of the side, the right side, out using multiplication. So we're going to take the 4x and multiply through by it. So this is going to be negative 4x cubed plus 8x squared plus 4x then we're going to multiply through by the negative 8, and this would be plus 8x squared minus 16x minus 8. All divided by x squared minus 4x plus 5 cubed. Well, let's continue this on the next page. So this gives me negative 2x cubed plus 10x squared minus 18x plus 10 minus, let's simplify what terms we have. So I have negative 4x cubed. Looking at the x squareds, I have 8 and 8, which is 16x squared. And then we have 4x minus 16x is negative 12x, and then minus 8. All over x squared minus 4x plus 5 cubed. And now we distribute the negative. So it's negative 2x cubed plus 10x squared minus 18x plus 10 plus 4x cubed minus 16x squared plus 12x plus 8. All divided by the same denominator. And now we simplify. Looking at the x cubed terms, I have negative 2 plus 4. That's positive 2x cubed. Then we have 10x squared minus 16x squared is negative 6x squared. Looking at the x terms, I have negative 18 plus 12. That's negative 6x. And then 10 plus 8 is 18. And that's the second derivative. Let's put a little box around that. All right, so that's our second derivative that we can use to solve the rest of the problems. There are a couple of things that we need to know. First is, where is f double prime undefined? I'll go ahead and dispense with that because that one's easy. And then we need to know where it's equal to 0. Well, f double prime is undefined where the denominator is equal to 0. But the denominator is the same denominator from the very beginning. And we decided that this denominator, when it's set equal to 0, has no solutions. So therefore, there are no places where this second derivative is undefined. So now let's turn our attention to, where's the second derivative equal to 0? Well, the second derivative is equal to 0 when the numerator is equal to 0. And now you have to factor this one. This one uses a factoring technique called grouping. And we can tell that it's grouping by looking at the ratios of the terms that I'm underlining here. If you look at those, you can see that it's a 6 and a 2. So 6 over 2 is 3. 18 over 6 is also 3. And they need to have the same signs with the ratios as well. One's negative, one's positive. So it would technically be a -3 ratio. But they're both the same, so we can factor this by grouping. So the way you group factor by grouping is you take the first two and group it like that. And then you take the second 2 and group it together as well. Now notice what I did with the negative. I left the negative with the 6 and put a big plus in the middle. These terms are still added. They're not multiplied yet. And so the negative with the 6 needs to stay with the 6 in this case. Now the way grouping works is first figure out what you can factor from these first 2 terms here. So I've got a 2 and a 6, so I can factor out a 2. I've got x cubed and x squared, so I can factor out x squared. That leaves behind x minus 3. Then the question is, what can you factor from the second pair? And I see I can factor out a negative 6. When I factor out negative 6, that leaves behind x minus 3 as well. And that's the key to grouping. If you leave behind the same factor, then you can factor that factor out, and pull that out, and then what you're left with comprises the other factor. So this factors as x minus 3 times 2x squared minus 6. Now we set those equal to 0 and solve for x. So x minus 3 equals 0 gives me x equals 3. And 2x squared minus 6 equals 0. Move the 6 over. You get 2x equals 6. 2x squared equals 6. Divide by 2. You get x squared equals 3. And so x is equal to plus or minus the square root of 3. And these are the 3 numbers that are the solutions to the second derivative when it's equal to 0. Let's go ahead and make a sign chart for the second derivative. And the order that these come in, well, negative root 3, that's the only one that's negative. Now I have to decide which one is bigger, root 3 or 3. And the answer is 3 is the bigger of the two. And so root 3 goes in the middle. And I can do my testing. So these are all zeros. And I can do my testing. Let me test at 0. And when I test the second derivative at 0, I get a positive. And all the multiplicities were 1, so they alternate, and that is the sign chart. And if you're still not comfortable using multiplicities, you can test points at every interval, no problem. What we do now is we make the statement. So f is concave up on negative root 3 to root 3 union 3 to infinity. F is concave down on negative infinity to negative root 3 union root 3 to 3. And then f has inflection points at, and I'll just list the x's. X is equal to plus or minus root 3 and 3. And there you go. That was a toughie. The second derivative test is used to determine when we have a critical value that is a relative max or a relative min. The second derivative test says the following. Suppose f double prime of x exists on an open interval and x is equal to c is a value inside that interval where f prime of c is equal to 0. So in other words, c is a critical value or a critical number. Then here's the test. If you evaluate c inside of the second derivative and it's positive, then you have a relative minimum. Well, that's because if you have c as a critical value where the derivative is equal to 0, that's a horizontal tangent line. And so you have a point where we have a horizontal tangent line, but around here we have concave up. So because it's concave up, it forms a little bowl shape. And then we have the point C, and then where we have a horizontal tangent line. And so therefore, that's a minimum. Similarly, if you evaluate the critical number in the second derivative and get a negative, that means it's concave down and produces a relative max. So it's the same idea. Here's the point. Here we have another horizontal tangent line. And so this must form a maximum. Now, if the second derivative is equal to 0 at c or it's undefined, then we say that the test is inconclusive. It doesn't mean that it isn't a relative min or max. It just says that we don't know. And so it still could be, you just don't know. Example number 5. Determine the relative extrema of f of x is equal to x squared times x minus 1 cubed by using the second derivative test. So first we need to find the critical values. We find critical values by taking the derivative. We're going to use the product rule here. So this is going to be the derivative of the first times the second unchanged plus the derivative of the second, I'm using the chain rule and the power rule together, times the first unchanged. We're going to set that equal to 0 and solve for x. In order to solve for x, I need to factor some things out. So I've got an x that I can factor out, and I've got x minus 1 squared that I can factor out. That leaves me with 2x minus 1 plus 3x equals 0. Now the advantage of having it in this form is that it's already factored. And so we're going to get, I can simplify it one more step before I split it up. So it's going to be x times x minus 1 squared times 5x minus 2. And you can see where the 5 come from. The 2 distributes, adds to the 3x, and we get 5x. Now we can split this up. So I get x equals 0, that's a critical value. X minus 1 squared equals 0 is going to be x equals 1. And 5x minus 2 equals 0 is going to be x is equal to 2/5. So those are our 3 critical values. We're going to use the second derivative to test those to see if they're maxes, mins, or maybe we don't know. So let's find the second derivative. I'm going to find the second derivative by taking the derivative of this version of the derivative. Now it's a little complicated because it's a product, but it does have 3 terms. So what you can do is you can sort of group them together. And my grouping is going to be these first 2 is one thing, and then the x by itself will be its own thing. So let's see how that works. So f double prime of x is going to be the derivative of the first. Well, the first is just x, so that derivative is 1. Times the second unchanged. So that's all of this by itself. Plus the derivative of the second. Now this is where it gets a little complicated. The second one is actually a product. So I'm going to have to take the derivative of that as its own little product. So it's a product rule inside of another product rule. The derivative of this is 2 times x minus 1 times 1 by the chain rule times the second piece unchanged plus the derivative of the second piece, which is just 5, times the first unchanged. Then we multiply all that times the original first, the x, on the outside. And this is what we must simplify. So I'm going to factor out the x minus 1. And from this first piece here, it's going to leave an x minus 1 times 5x minus 2. Plus, from this piece right here, it's going to leave 2 times 5x minus 2. And I'll go ahead and bring in the x from the outside. And then I want to look at this piece, and that is going to still have a 5, the x from the outside, and 1 factor of the x minus 1. Okay, good. Now, let's simplify the inside here. I'm going to use FOIL on this left part here. This is going to be 5x squared minus 2x minus 5x plus 2 plus 10x squared minus 4x plus 5x squared minus 5x. That's going to be x minus 1 times, I've got 5x squared, 10x squared, and another 5x squared. So that's 20x squared. I've got negative 2x, negative 5x, negative 4x, and another negative 5x. That's 7 and 9 is negative 16x. And then I've got plus 2. Now, we're not really solving for when this is equal to 0, so that's a good thing. We just want to use it to test our values. So now we test the critical numbers. In the second derivative. So let's see what that looks like. So we're going to do f double prime of, one of our numbers was 0. So this is going to be 0 minus 1 times 20 times 0 squared minus 16 times 0 plus 2. So that's negative 1 times 2, which is a negative. Since it's negative, that means that the function is concave down at that point, and this 0 must be a maximum. So that means we have relative max at x equals 0. All right, let's test 2/5 next. And so this would be 2/5 minus 1, and 20 times 2/5 squared minus 16 times 2/5 plus 2. And that is equal to a positive. I worked it out on the side here. And so since that's positive, that means the graph is concave up in that area, but at 2/5 we have a critical value, so that must mean we have a relative minimum at x equals 2/5. All right, and then finally, let's test at x equals 1. Well, that's bad news. At x equals 1, we get 1 minus 1 times all of this, which is equal to 0, because this term is 0. That means the second derivative test is inconclusive. So you would have to go back to sort of your old way of figuring out if this is a relative min or max by testing points around it. And so let's see. If we test on the right side of 1 in the first derivative, let's test at, say, 2. So 2 times 2 minus 1 squared times 5 times 2 minus 2, that's positive. And then in the second derivative, the multiplicity was equal to 2. So that means it's going to be positive on the left side of 1 as well. And that means it is not an extreme value, because the curve is going up and then continuing up. So it's one of these where it sort of flattens off and then continues up without making an extreme value. Lastly, we turn our attention to the business topic of point of diminishing returns. And the idea is basically this. When you start spending money, let's say on advertising, for example, then you end up with increased sales. And so sales always increases, as you spend more money on advertising. You can't advertise to end up with decreased sales. But the question is, how do the sales increase as you go through more advertising money? And as they increase at a certain rate, and then they sort of level off again, right? So they start out and they start rising and they get more steep, and then they sort of level back off, and they still increase, but they're not as much as they used to. Well, the point where it changes from increasing at its steepest point to where it's just slowing down its increase, that's called the point of diminishing returns. And the term comes from the fact that as you put more money into the advertising, you're not getting as much back out of that money. You're still getting an increase, but you're not getting as much of an increase as you were. So let's take a look at this example number 6. A company estimates that sales will increase from 1,500 stereos to n of x equal to 4x cubed minus 0.2 x to the 4th plus 1,500, with x from 0 to 14, where n is the number of stereos and x is thousands of dollars spent on advertising. Find the point of diminishing returns, and what is this max rate of change in sales? So if we're looking at the graph, what we want to find is, when does the rate of change sort of turn over? And that is equivalent to an inflection point. And so that's what the point of diminishing returns is asking for. What is the inflection point? Well, to find the inflection point, we need the second derivative. So let's start by taking the first derivative. And then the second derivative is 24x minus 2.4x squared. And we need to solve for when this is equal to 0. So if I factor out 2.4x, I get 10 minus x as one of the factors. If we set both of these factors equal to 0, I get x equals 0 and x equals 10. Well, x equals 0 is the very beginning, no change in advertising sales at all, or advertising money. So that one's out. And so 10 is going to be the inflection point. We just need to check to make sure that that's the appropriate spot, and yes, it is. You can see how the slopes are increasing to that point, and then after that point, the slopes start to decrease. And we're not talking about the graph itself, we're talking about the slopes of the tangent lines, which is the rate of change. So the inflection point occurs at 10, which is $10,000 in ads. The last question is, what is the max rate in change of sales? So the max rate in change of sales, well, the rate comes from the first derivative. Let me rewrite that here. And to find the maximum rate, we know the maximum occurs at the inflection point, so that would be 10. So n prime of 10 would be 12 times 10 squared minus 0.8 times 10 cubed. And that's equal to 400. Now the question is 400 what? Well, this is equivalent to dn dx. And the n is stereos sold per, and the x represents thousands of dollars in ads. So that means for every $1,000 in ads, you're gaining an additional 400 stereos in sales at the maximum rate where the advertising is increasing your sales. That would be equivalent to this tangent line right here. If I can draw it, there it goes, right there, just like that. Yeah. And so that's the maximum rate that you can produce more sales for the money. So after spending $10,000 on sales, the more money you spend, the less of a bang you get for it, because that's not resulting in more sales at the same rate that it was before. You're still getting more sales. It's just not producing as many more sales as it was before that and maxed out at $10,000.